All right, well, good morning, everybody. So we're going to begin today by talking about the midterm exam. I will note right off the bat that the class as a whole did significantly better than on the first exam. The average was about 46.5 out of 60, which is, in the upper part of the 70% range, so that was good. On the previous exam, the average was 42, so almost a full letter grade higher on this one. I still had a big spread in the scores. The low score was 17, and I don't think anybody got 60 out of 60 on this one. 59 looks like the highest. Nonetheless, if you're trying to figure out your grade, 90%'s an A, 80%'s a B, et cetera, et cetera. So let us just spend a few minutes talking about the exam. Make sure we know what we did right or wrong. They're all alphabetical. All right, so the first problem was clearly an ideal gas mixture problem, and you were just asked to find various parameters associated with that particular mixture. To make things go more quickly, I had given you a variety of molar mass data and gas constant data, although admittedly I had a typo and I wrote down the wrong molar mass for argon, but I hopefully fixed that at the beginning of the exam. If you did it using the numbers given, you still would get full credit for that. So the first thing we need to do is recognize that we need mole fractions, and we know that the mole fractions are going to certainly be related to the various pressures, right? Partial pressures. We know that the mole fraction is just the partial pressure divided by the mixture pressure. So we can find the mole fraction for neon. Again, it's just the pressure over the mixture pressure. So we're given 20 kilopascals. The mixture pressure is just going to be the sum of all the various partial pressures. So that's just going to be 160 moles. 160 kilopascals. So basically we get 0.125 for the neon, and using the same equations for the argon and the xenon, we have 0.25 and then 0.625 for your various mole fractions. Okay. Now that we have the mole fractions, we can find the number of moles. So we know the number of moles is just the mole fraction and then multiplied by the number of moles of that particular mixture, right? So, let's call this Ni, this is Y, and M, okay? So again, we'll just use this to calculate the various values for the neon and the argon and the xenon. So, again, we know the total number of moles of the mixture. You're told that it's 250 in the problem statement. So it's just a matter of going through the mathematics here, and we get 31.25 for the neon, 62.5 for the argon, and 156.25 kilomoles for the xenon. And now that we have the number of moles, it's pretty easy to calculate the mass of each component. We know the mass of each component is just the number of moles times the molar mass of that particular component. Again, you're given the molar mass data, so we can find our various masses. Again, we know the number of moles, we know the molar masses, so we get 630.72 kilograms of neon, 1871.75 kilograms of the argon, and 20,515.625 kilograms of the xenon. And of course, we are going to need to sum these to get the total mass of the mixture, and that's 23,018 kilograms. Now, let me note that these numbers that I'm putting on the board are going to be a little bit off compared to what most of you have done. Please note that I'm taking into account my typo. that I assumed the incorrect molar mass, specifically for the argon. I used 39.948 instead of 29.948. So, just keep that in mind. This is reflected in my solution here. I'll give you correct numbers here in just a moment. Anyway, so we have all these various masses and the total. Now we can find the molar mass of the mixture, just as the mass over the number of moles, and the gas constant of the mixture as the universal gas constant divided by the molar mass. So we can look up the universal gas constant in the inside back cover of our book, and we end up with 92.072 kilograms per kilomole as the molar mass, and 0.09030 kilojoules per kilogram per Kelvin for the gas constant for the mixture. And then last but not least, we could just use our ideal gas equation of state to get the temperature of the mixture. We know the mixture pressure, we know the total volume, we know the mass now, we know the gas constant, so we could just calculate this. And we get 769.8 Kelvin. So here's the results that we're looking for. Okay. Now again, if you use the correct molar mass, then the mass of, let's see, I guess the mass of the argon is the one that was in error. So again, if we use the right numbers, it would be 2496.75 kilograms for the mass of argon. Maybe I'll just put these in brackets. The total mass, of course, is then going to be different. It's going to be 23,643.1 kilograms. So again, if you use the right data. And then the molar mass is going to be off a little bit. We're going to get 94.57. And the gas constant is going to be 0.0879 with the same units as shown over here. The temperature is not affected by the incorrect molar mass that I gave you. Nonetheless, these are the results that we're looking for. Pretty straightforward problem. As far as the grading goes, first just noting that the total pressure is the sum of the partial pressures of 160, so that's just worth a point right off the top. 4 points for finding the correct mole fractions and then the number of moles, so that's a total of 5. A total of 4 points associated with calculating the mass of each component and finding the total mass. Then just using that data properly, 2 points for the molar mass, 2 points for the gas constant, 4 points for the temperature. Let me also note that there are multiple ways to do this problem, as I mentioned many times with these. This method is just one of many possible methods. For instance, you could have used the number of moles and then multiplied it by the universal gas constant in the denominator to get the temperature of the mixture. You would get exactly the same result. There's other ways to do some of these other previous calculations. I'm not going to get into all those. But nonetheless, there's problem number 1. So any questions on this one? Okay. Problem number 2 is an atmospheric air problem where you're simply required to find various values like the relative humidity, absolute humidity, et cetera, et cetera. So you're given in the problem statement the partial pressure of the water vapor as 1.09 kilopascals. You're also given the total pressure of the atmospheric air, so that's P of 100 kilopascals. And to find the partial pressure of the dry air, we just have to subtract the total pressure, subtract the partial pressure from the total pressure. So we get 98.91 kilopascals. So that's really the best way to start, is just to get all of this data. We also have other data we're going to need. So for instance, at 25 degrees Celsius, we need to go into our steam tables, our water tables, if you will, and find some data. One thing we're going to need is what we call PG, which is just a saturation pressure at this particular temperature. So this is 3.1698 kilopascals. And then we're also going to need the enthalpy of the water vapor. So again, this is just Hg at 25 degrees, and that's 2546.5 kilojoules per kilogram. So this is how we start the problem, and now it's really just a matter of plugging numbers into our various equations. So the relative humidity is the partial pressure of the water vapor divided by what represents the maximum possible partial pressure of that water vapor at that given temperature, right, the PG term. So we just find this, and it's 0.3439. You can express it as a percent if you want. We can find omega pretty easily. That's just 0.622 times PV over PA, or if you will, PV over P minus PV. Nonetheless, we have this, and this is 0.006855 kilograms of water vapor per kilogram of dry air. Quite a few students forgot the units on this omega term. Then the mass fraction of the water vapor is just omega over 1 plus omega. So this is 0.006808. And this is the mass fraction of water vapor in the mixture, so really should be kilograms of vapor per kilograms of the atmospheric air, that is of the mixture. A lot of students also forgot the units on this one. And then last but not least, if we want the enthalpy of our mixture on a per unit mass of dry air basis, then we would use this particular equation. Keep in mind that HA is just what 1.005 and then times the temperature, and that temperature has to be in Celsius. Okay, this was explained in class when we were talking about this. Quite a few students converted that into Kelvin, in which case you got the wrong answer. But nonetheless, that's the HA term. And then we have omega, so 0.006855. And then multiplied by Hg. Now you could have either used the equation that was presented in class and is in your textbook, or it's probably easier just to use the value of Hg. You already pulled it out of your book. So we go through our mathematics, and we end up with 42.58 kilojoules per kilogram of dry air. So there's your last term. So as far as the grading goes on this one, 2 points for correctly finding the partial pressure of the dry air. Another 2 points for knowing that PG is the saturation pressure at the given temperature. Another point for pulling the enthalpy data out at the proper temperature. And then lastly, 2 points for everything else. 2 for finding phi for omega for the mass fraction. 2 for finding H of the dry air using that equation with the right temperature in Celsius, and then 2 points for finding the enthalpy of the mixture. So a total of 15 on that one. So any questions on that problem? Good. Last but not least, of course, is going to be problem 3, which is your Rankine cycle problem. So this problem was certainly longer than the rest, and for that matter, it was also worth more points than any of the rest. It was a pretty straightforward problem, but some students had issues, so let me go over this one as well. Again, I gave you a variety of data. I gave you the data you needed at points 1 and 3. I gave you the data you needed at point 5, so that probably saved you at least 5 minutes or so just pulling data out of your tables. Let's keep in mind that the first thing we'll calculate is H2. So this is just going to be H1 plus the specific volume at 1 times the pressure difference. And we're going from, 2 psi up to 1750. And note also that the units here are definitely wrong. We would have psi a foot cubed. We have to convert it into BTUs. So we definitely also need to divide by 5.40395. The specific volume, again, I gave it to you. I'm not going to write it down. Go through our math, and we end up with 99.27 BTUs per pound mass. And then we're going to do exactly the same thing as we find the enthalpy at 4. So this is H3 plus V3 delta P. Here we're going from 1750 up to 3500. We have to use the appropriate conversion factor. Nonetheless, we end up here with H4 of 650.14 BTUs per pound mass. So we now have H1, 2, 3, and 4. H5 is given. So now let's go from 5 to 6. So we recognize that it's an isentropic process. So at S6, which equals S5, And at the pressure at 6, which is the intermediate pressure of that feed water heater, right, 1750, it is still superheated. I mean, I'm sorry, it's not superheated. It's no, it is superheated, right, at 0.6. Yeah, so in fact, even on the diagram, you can see that I showed 0.6 as being to the right of the saturation line. So you could have also just done the usual test. You know, this entropy is actually greater than SG at the given pressure P6. So I mean, clearly this is superheated vapor. So we go into A6, well, A6E technically, and we can pull out the enthalpy we need, 1264.5. In fact, I was, spent quite a few minutes trying to find some property data in your tables such that the entropy at 5 was essentially equal to the entropy at 6. I mean, they were off by like, what, two 10,000ths or something like that in the tables. So you could have just pulled the data directly at that entropy at 5 and at that pressure at 6, and, you'd get something like this. Maybe you get 0.7 or 0.6 at the end. Nonetheless, this would be how you'd find the enthalpy at 6. And then we continue to 7. So now at S7, which also equals S5, and at P7, well, here we definitely have a two-phase mixture, so we have to go into table A5E. We have to use our entropy data in order to get the quality. I'm not going to go through all the math here. We've done this a million times. We end up with a quality of 0.7083. And then we use the quality to get the enthalpy, HF plus X times HFG. So again, I'm not going to plug in the numbers, but we get 817.7 BTUs per pound mass. Now we have all of our enthalpy data. Continuing, all we really need to do now is apply the appropriate equations. We know that since this is a regenerative Rankine cycle with a single open feed water heater, that we had better do our energy balance on the feed water heater. So the energy balance tells me a YH6 plus 1 minus YH2 equals H3. So this is our energy balance, our first law, if you will, for steady flow process. And plugging in the numbers, we get y equals 0.466. And then lastly, we just have our various equations. So the thermal efficiency is going to be the net work over the heat input. Basically, we have H5 minus H6. Then we draw off the fraction. So now we have 1 minus y, H6 minus H7. And then we have our pump work that we have to subtract from that. So we have the fraction 1 minus y as we go from 0.1 to 0.2. And then we combine back in the extraction steam, and we have an H4 minus H3. And this then will be the full flow from 3 to 4. So that's the numerator. And then in the denominator, we only have a single heat input term, H5 minus H4. So if we plug in the numbers, we end up with 301.16 in the numerator, 687.66 in the denominator, or 0.438, which again we can express as a percentage if we wanted to. And then lastly, you're asked to find the power, which is the rate of doing work. Well, you're given the mass flow rate. The net work is just the numerator from the equation above. So just throw your numbers together. We get 2.71 times 10 to the 8th BTUs per hour. If we wanted to, we can convert to horsepower, 1.065 times 10 to the 5th horsepower. Some students had the results in BTUs per second. Any appropriate units would be okay. So there's your final problem on this exam. 3 points for knowing how to calculate H2. 3 points for knowing how to calculate H4. By the way, you could have actually used A7, that is table A7, the compressed liquid tables for some of this, like from 3 to 4 you could have. But it's a whole lot easier just to use the V delta P. Anyway, then 3 points for knowing how to get from 0.5 to 0.6. 4 points to get down to 0.7, 5 points for having the right energy balance and calculating the extraction steam flow fraction appropriately. I assigned 7 points to the thermal efficiency equation. I mean, there's basically 7 terms. So, you know, if you had all the right terms in there, then you would have gotten full credit. If you missed some things like the 1 minus y's, or, you know, maybe some of your enthalpies weren't quite right, it could have cost you some points. And then 3 points at the end for calculating the power. So, total of 28. So again, any questions on this particular problem? Okay. So those of you coming in late, the exams are up here at the front. Please don't forget to pick yours up. The high was 59 out of 60. The low was 17. The average was about 46 and a half, 47, that range. So in general, the class did very good. So again, any last questions? All right. So let me put your homework on the board. And in fact, we really only have 1 day of instruction next week. Monday's a holiday for Memorial Day. Friday is a review, Q&A day, and all that. So I'm not going to break this out into homework sets 9 and 10. Let's just call it our last homework set. And it's these problems. So here's your last homework set. Let me also note that the homework from last week that you're turning in on Wednesday is actually going to be the last homework set that I'm going to grade. You're certainly still responsible for this last homework set, but frankly, I always like to post the homework, you know, at least a week before your final exam, and things get so busy and hectic near the end of the quarter anyway. I'm just not going to collect the last couple of homework sets, or actually this last homework set for this and next week. Again, make sure you understand how to do the problems. The solutions will be posted no later than a week from Wednesday. Okay. So let us now go back to what we were talking about last time. So now we're talking about air conditioning, right? And hopefully you can see that we're bringing together various concepts and topics that we've been talking about really for the last half a year or so. You know, we are having to add or remove heat. That kind of implies the first law. There's mass that's being added or removed, so that implies a continuity equation, or if you will, conservation of mass. We've got lots of different possibilities. We certainly have to look at all of our problems in the context of air-water vapor mixtures and using data for air-water vapor mixtures. So that's certainly being brought in to these types of problems. So a lot of information is now being considered. So far, we've only really looked at the simple heating and cooling types of processes. If I were to show this on the psychometric chart, and that's typically how I'm just going to show the psych chart, then if we have a heating process, we're simply moving horizontally to the right. Remember, this is the actual temperature called the dry bulb temperature versus omega. So as we heat, we're not adding or removing humidity, so we're simply moving horizontally on the psych chart. On the other hand, if we have a cooling process, then again, we're not really removing any moisture or adding any moisture. All we're doing is cooling. So omega is going to be constant. We just have a horizontal line. And the first law equations, if we have a heating process, it's just the air mass flow rate times H2 minus H1. And if we have a cooling process, the rate that heat is removed is just the air mass flow rate times H2 minus H1. I'm sorry, H1 minus H2. Okay, so this is going to give you the rates of heat output or the rates of heat input for a heating or a cooling process. So this is what we really finished talking about last time. Okay. Please note that the enthalpy data is for the mixture. I know I'm repeating myself a lot on this. But even though it's enthalpy for the mixture, it's still given as energy per unit mass of the dry air, right? So that's why we have to multiply by the dry air mass flow rate and not the mixture flow rate. All right, so what about other situations? What if we have a situation where it's not only too cold, but the air is also too dry? Okay. So one thing we might note, and let's just look at simple heating for a moment. As we heat up the air, the relative humidity drops, right? The relative humidity would be represented by these angled lines that basically start at the horizontal with relative humidity of 0 and go up to 100% along the saturation line. But you can definitely see that as we heat, the relative humidity phi is going to drop. So in heating air, it actually becomes more uncomfortable because of the dryness of that air. So it's very common when we have a heating process to actually add humidity as well. So the next case we're going to look at is heating with humidification. Okay. And when we look at a heating with humidification process, we're really looking at two processes that occur one after the other. So let's say we have state point 1 as our atmospheric air, and first we're going to heat it. So I'll just show some sort of a heating coil, and then there's going to be some heat that comes in. So we're going to end up at a state point 2. Okay, so this is going to be the heating process. And then after the heating process is over, then we'll have a separate process, which is the humidification process. And in this humidification process, we're going to have some sort of water or steam. It really just depends. And this water or steam is going to come in through a series of spray nozzles and will actually be sprayed into that, well, airstream. So we'll just call this point W, W for water that's being sprayed in. But clearly, as the atmospheric air moves out of the heating section and into the humidification section, it's going to pick up moisture. So we move through, and eventually we come out at some state point 3. So all 4 of those state points need to be recognized as we look at this type of problem. Next, what would this look like on a psych chart? Well, part of it we know. I mean, clearly from 1 to 2, it's just simple heating. So we'll just illustrate this as a 1 to 2. However, as we add moisture, it really depends on whether we have liquid water or water vapor that we're adding. If we're adding liquid water, that liquid water is going to go into the airstream, but it's going to have to change phase, so energy is going to have to come out of the airstream. And as such, we're going to be adding moisture, but at the same time, reducing the temperature. So adding liquid water, we're going to tend to move in that general direction from point 2 to point 3. Okay. On the other hand, if we have water vapor that's being added, let's say steam, typically steam is going to be at a temperature that's higher than the ambient temperature. So not only are we going to add water vapor, but we're also going to increase the temperature of the atmospheric air, and we'll end up with something that's more over here. Okay, so that line would represent steam in, as opposed to liquid water in. And in fact, we could be anywhere in between, right? I mean, it depends entirely on the thermodynamic state of the water that's coming in as to where we are exactly, which line we're on. I'm just going to put that little curved line with an arrowhead on both sides just to represent that we could be anywhere in that particular, anywhere in that particular location. So this is the process. Now let's look at the appropriate equations, and just like we've done before, we're going to have to look both at our mass balance as well as our energy balance, our first law. So we'll start with the mass balance. And again, like we've done before, we're going to separately look at the dry air and separately look at the water. Okay. Well, first the dry air. That one's always easy, right? We know that there's a certain amount of dry air coming in at 1. We know that that mass of dry air is not going to change. Yeah, we're going to add or remove humidity, in this case add humidity, but we're not changing the flow rate of the dry air component. So the amount of dry air that comes in at 1 is the same as that which moves through the center of the device at 2. It's the same as what leaves at point 3. We're just going to call it m dot A for dry air. So this is our dry air term that we have. Next, we would have our energy balance term. I'm sorry, not energy, that's next. Next, we'd have our water mass. Now here, we would note that there's really 2 processes, from 1 to 2 and then from 2 to 3. So we have to identify each one separately. We would note that from 1 to 2, we're not adding any liquid water or water vapor. We simply have however much water vapor was in the air coming in at 1, and then that would have to equal however much water vapor is in the air at 2. Now, what comes in is m dot A omega 1, right? Omega is the specific humidity, again, called absolute or relative, absolute humidity or humidity ratio. This is a ratio of water vapor to air. So if we multiply the dry air by the ratio of water vapor to dry air, well, dry air cancels, we get the rate of water moving in. So however much water vapor comes in at 1 had better be equal to the amount of water vapor that's moving through to point 2. Again, no water is condensing, no water is being added. It's just a constant value. In fact, you can also see that the air mass will cancel, and then omega 1 equals omega 2. I mean, again, we know this, right? This is just obvious to us. It's been stated earlier today. So that's an equation we have. From 2 to 3, things are a little bit different. We have m dot A omega 2. That's the water vapor that comes with the air moving at 2. But then we're adding water, right? And this water is going to have a certain amount of mass associated with it. So here's the water coming in with the air, the mass coming in as water. I'll just call m dot W, W for water. And then that's going to equal the amount of water vapor that leaves with the air, right? So m dot A omega 3. So the water vapor coming in plus the water that we add has got to equal the water that goes out, or really water vapor that goes out. So there's my equation. And then typically we just modify this ever so slightly. We'll call it m dot water is just going to be m dot air and then omega 3 minus omega 2. Okay, so these are our mass balance equations. And now our first law, our energy balance. So again, we have 2 processes, right? From 1 to 2 and 2 to 3. So we'll do 1 to 2 first. And this is just simple heating, right? This is no different than what we just looked at before. So as this is simple heating, I'm just going to use the equation that's already written over there on the board. Q dot in is just m dot A H2 minus H1. However, as we go from 2 to 3, well, then things are certainly going to be just a little bit different, right? So there's a certain amount of energy coming in with the air, right? We know that this is our first law, the sum over all inlets, m dot IHI equals the sum over all exits, m dot EHE. So we would just look at that, and we would note that, well, what's coming in? So we have m dot WHW, so this is the liquid water that's coming in between points 2 and 3, and this will be the enthalpy term, right, m dot times H. We have a second inlet term, right? That's the enthalpy associated with the atmospheric air that's moving through at point 2. So this is m dot AH2. Okay, so this is our inlet. And then at the exit, there are, well, there's only one stream. So that's just going to be m dot AH3. And then this equation can be modified ever so slightly as well. Typically, what we would do is we would plug in this water term. So we're going to plug in that m dot A omega 3 minus omega term into the equation above. We get m dot A omega 3 minus omega 2 HW, and then plus m dot AH2 equals m dot AH3. You can see that the air mass flow rates cancel. And rewriting this, we would get omega 3 minus omega 2 HW plus H2 equals H3. So this is the energy balance that we would have. So this equation, these equations, these are the equations we're going to use in our analysis. Yeah?
In the energy balance equation, how are we taking into consideration the energy that is brought by the water vapor in the air initially and the final water vapor when it's...
Well, I mean, that's what the H1, H2, and H3 terms are all about, right?
But isn't that the energy for dry air?
No, no. I mean, these are mixture enthalpies. I mean, HW is obviously just water, but no, H2, H3, H1, those are the enthalpies of the mixture, but per unit mass of the dry air. So this is something that is clearly confusing. It's confusing to everybody at first. Just keep looking at it long enough and you'll figure it out. But yeah, basically all these enthalpy terms, 1, 2, and 3, are enthalpy of the mixture, the air-water vapor mixture, call it the atmospheric air if you want, but per pound or per kilogram of the dry air. That's just how the data is presented to us. Okay. All right. One thing I might want to note here too is that implied in many of these equations above, if we want to know something about the rates, for instance, if we want to calculate the rate of heat input, well, we would just use this equation, which is the same as this equation. But we would need to know the mass flow rate of the air, right? Also, I might note that we'd be interested in knowing how much water supply do we need. I mean, this process is not going to work unless we have the right amount of water being added. So we have to have an appropriate water supply, and we can calculate it using this equation. We need to have an appropriate heat supply. We can calculate that using that equation. But in either case, we're going to need data for the air mass flow rate. So having m dot for the dry air or the volumetric flow rate of the atmospheric air. Please note that if we have the volumetric flow rate of the atmospheric air, then the mass flow rate of the dry air is just the volumetric flow rate of the atmospheric air divided by the specific volume of the atmospheric air, right? And keep in mind that, like all the data, specific volume is per unit mass of the dry air, right? So the volumetric flow rate of the moist air, the atmospheric air, that'd be what? Cubic feet per second of atmospheric air divided by cubic feet per pound mass of atmospheric air, cubic feet of atmospheric air per pound mass of dry air. This is going to give you the dry air mass flow rate. So having the air mass flow rate or the volumetric flow rate of the atmospheric air, now we can find the rate of heat input, and we can also find the rate that water needs to be added. Okay? We need to provide those, right? We need to have an appropriate heat supply. We need to have an appropriate water supply, and that's why I just like to bring up these equations. Another thing I want to note, and this is not actually presented in the textbook, I'm not sure why, what we would find is that typically the unknown for this problem is going to be HW. We want to know what temperature of water we need for this particular air conditioning process. So I would note lastly then, to find the temperature of the water that's required, we would again just go to the energy balance equation. Okay, so this is the equation I have underlined over here. We would use this particular equation and we simply solve for HW. I mean, keep in mind, we will typically have all of our psychometric data based on the problem statement. We will have the ability to look up omega 2, omega 3, H2, H3. I mean, this is data we will have. So we'll be able to solve this for HW. And then, if it's liquid water, then the temperature of the water is just going to be the saturation temperature at the enthalpy of the water, which we'll assume is a saturated liquid at HW equals HF. So you would know HW, you would just go down the HF column in table A4, and you would find the value that gives you the appropriate temperature. So that's the temperature of the water supply you would need for this particular problem. On the other hand, if we had water vapor, then the temperature of the water is just going to be the temperature at Hg at whatever the pressure of the steam supply is. Okay, so if you know the enthalpy of saturated vapor at an appropriate temperature, which is typically the data you would have, well, again, you've calculated HW, right? Maybe I should say Hg at the pressure of the steam is my HW term. But having calculated HW, we can again go into our tables. This time we'll have to look down the saturated vapor column and find the value of Hg that's shown in the tables, and then just find the appropriate temperature that corresponds to that pressure. So again, this is something you would just have to keep in mind. So questions on that? All right, I would like to do an example problem. And just give me a second. So let's see, this one is from your textbook. It's 14-72. And here's the problem. Okay. All right. So here's the example problem we're going to look at. This tells us that we have air, although I suppose the author could have used the word atmospheric air. But nonetheless, air at 14.7 psia and 35 degrees Fahrenheit, 50% relative humidity is first heated. It's heated up to 65 degrees Fahrenheit in the heating section, and then it's humidified by introducing water vapor. The air leaves the humidifying section at 75 degrees Fahrenheit and 55% relative humidity. So we want to find the amount of steam that's added in a pounds of water per pound of dry air basis. We want to find the amount of heat transfer to the air in the heating section, again on a BTU per pound mass of dry air basis. You look at that which has been requested, and it might sound a little bit odd, but it's not really that odd. I mean, for instance, if we just divide out the air mass flow rate in this equation, which is our simple heating from 1 to 2 in this particular problem, then that's going to give you the heat per unit mass of dry air. It's just going to equal the difference in the enthalpy. We can do essentially the same thing here. If we want to know how much water is being added per unit mass of dry air, we just divide out the m dot A, and that's going to be just omega 3 minus omega 2. So those are what we are looking for. Now, frankly, in this particular problem, if the author had given us the actual mass flow rate of the dry air or the volumetric flow rate of the atmospheric air so that we could calculate the dry air mass flow rate, well, then we could just plug in the m dot A terms, and then they would have asked us specifically for how much or what is the rate of water vapor being added or what is the rate of heat input. But based on the equations that were developed, unless we have that air flow rate data, which we don't, then everything has to be on a per unit mass of air basis. Okay. So with all this in mind, let's now begin this problem. So first of all, let's just identify all the data that's been given. Even though, at least in my mind, it's all pretty clear what we have, it's not always real clear. So first of all, the fact that it says air at 14.7 psia is the author's way of saying you can use a psychometric chart, our 14.7 psia psychometric chart, which is what table A31E, I'm sorry, figure A31E, way in the back of your book. And we're given a temperature and relative humidity. So T1 is 35 Fahrenheit, phi1 is 0.50. It says first it's heated to 65. So T2 is 65 degrees Fahrenheit. And then it's humidified, and we finally leave at a temperature T3 of 75 degrees Fahrenheit and a relative humidity of 55%, or just 0.55. Okay. So this is the data that's been given to us. The figure, well, I guess the figure is hiding behind the screen now. The figure we're going to use is exactly the same figure is already in your notes, so I'm not going to redo the figure. All the state points are exactly the same as what's in your notes. Now, what are we trying to find here? Steam added per unit mass of air. So basically from the equation m dot w equals m dot a omega 3 minus omega 2. M dot w over m dot a is really what we're trying to find. It's the ratio of the amount of water to the amount of dry air. So that's one of our unknowns. And then also Q dot in is m dot dry air times H2 minus H1, or if you will, Q dot in over m dot dry air, which is H2 minus H1. So again, this is the heat per unit mass of the dry air, which is the other thing we're trying to find. So that's the other unknown here. Now, if you look at these equations, all we really have to do is convince ourselves that we have enough data at each of those 3 points to solve these two equations. If I know any 2 bits of data, properties, right, then I can go into my psych chart and look up any of the other properties I want. So yes, I know 2 things at point 1, right? I know the temperature and relative humidity. I know 2 things at point 3. Again, I know the temperature and relative humidity. State point 2 is the one that might seem to be a little bit lacking, but it really isn't. Remember, simple heating from point 1 to 2, we're not changing the humidity ratio. So omega 1 and omega 2 are the same. So we really need to write that down, because without that, we can't finish the problem. Now, again, we know state point 1, so we can look up omega. Omega 1 equals omega 2. So yes, we have 2 points, right, omega and temperature at point 2. So again, we should be able to go into the psych chart and just look up absolutely everything we might need. So let us do that. We know the problem is solvable. So first at T1, phi 1, we go into our psychometric chart, A31E. And we really just need a couple of things. We need the enthalpy and the humidity. So here, you're all going to have to, get some practice on using the psychometric charts. Hopefully, many of you have just printed them off from, your access to McGraw-Hill's website, or printed them off from the property tables that are on Blackboard that I'd put there. Nonetheless, we go into the psych chart. We go to the 35-degree temperature, which is, say, right here. And we go up to the relative humidity, which let's say is right here. And we just read off the values, and we end up with H1 of 10.69 BTUs per pound mass of dry air. And again, your numbers might be off a little bit compared to these. I'll admit, I sometimes kind of cheat. There are plenty of electronic thermodynamic property tables and electronic psychometric charts out there. You just kind of have to hunt for them. But if you have one of those, then you just plug in any 2 numbers and push the right button, and it pops out everything else. So some of my numbers are going to be a little bit different than what you might get by looking at the psychometric chart. For instance, when I found omega, I got 0.002122. And this is going to be pounds mass water vapor per pound mass of dry air. Well, I mean, how can I go all the way down to the 6th decimal point on the psychometric chart? I mean, you're not going to be able to do that. Don't even try. Use the psych chart, do the best you can. If your numbers are close, you'll get full credit on any problem you'll turn in. Nonetheless, I cheat a little bit, but saves me a little bit of time. All right, so now we have omega 1. We note that this is equal to omega 2. So now, so let's see, it's simple heating. We heat the thing up to 65 degrees. So at 65 and at omega 1 equals omega 2, there's state point 2. So again, we just read off all the thermodynamic property data we need. So at T2, omega 2, back onto the psych chart. The only thing we need is the enthalpy. H2 is 17.93 BTUs per pound mass of dry air. And then lastly, we go to state point 3. So at T3 and phi 3, back into the psych chart, we get H3 of 29.16 BTUs per pound mass of dry air. And we're also going to need the humidity. So omega 3 is 0.01017 pounds mass water vapor per pound mass of dry air. All right, so now we have all of the equations that we're going to need. We have all the data we're going to need. Now it's just a matter of plugging all the numbers in. So I think in the interest of saving time, I'm not going to actually plug in the numbers. The equations are pretty straightforward. So the ratio of water to dry air is just omega 3 minus omega 2. And for that, we get 0.00805 pounds mass water vapor per pound mass of dry air. So for every pound of dry air that's moving through the system, we need to add 0.008 pounds of water vapor. And then with regards to energy, Q dot in over M dot A. This is H2 minus H1. And this number becomes 7.24 BTUs per pound mass of dry air. So these are the results that we're going to be looking for. So again, it should be pretty straightforward. I'm going to actually add to this problem ever so slightly. I would like to know what the temperature is going to be of the steam that's being added to this particular problem. Now, I didn't really show what's happening from 2 to 3 here, but I might note that since the temperature at 3 is greater than the temperature at 2, I don't know any way of doing that unless you're adding steam. I mean, I suppose if you added liquid water at a high temperature, that would also possibly work, but still, we're going to be moving from point 2 to point 3, and the temperature is going to rise. So, this is 75 degrees Fahrenheit here at state point 3. Let's find the temperature of the steam. So let's just continue with this particular example problem. Let's find the temperature of the steam if it comes in saturated at 60 psia. In fact, I shouldn't say saturated. I'm just going to say comes in at 60 psi. We don't really know if it's saturated in this particular case. All right, so how do we do that? Well, we have to go to the third of those equations that was derived just a few minutes ago. Omega 3 minus omega 2, HW, plus H2 equals H3. So let's just plug in everything we know. The only thing we don't know is HW. So I have omega 2, I have omega 3, I have H2, I have H3. If we just plug in all these numbers, we're going to end up with HW of 1395.4 BTUs per pound mass. And this is for the water, so this is per pound mass of water. I'll just put a little W there. And then, as it turns out, just the way I worded this problem, we know the pressure, and now we know the enthalpy. There's nothing that specifically says this is a saturated vapor. I could have changed this problem a little bit. I could have simply said, if it's a saturated vapor, then find the temperature. And when you found the enthalpy, you then just go down the Hg column, as I was actually explaining just a few minutes ago, and find out what temperature that corresponds to. Here, it turns out that it's superheated. At this pressure and at that enthalpy, we actually have superheated steam. So we're going to have to use table A6E, and we're going to have to go to the 60 PSIA subtable, and we're going to have to interpolate. And if we do so, we're going to find that the temperature is somewhere between 700 and 800 degrees Fahrenheit. We actually end up with 728 Fahrenheit. Okay, so in this particular case, because it's superheated, you would use the superheat tables. Although when I was mentioning the general equations previously, I essentially implied that we could assume it was saturated. It just depends on the problem. So maybe I shouldn't have earlier said assume saturated. Just assume whatever is based on the problem statement. In this case, because we're given a pressure, it's superheated. So any questions on this particular example? Okay. So the next thing that we need to do is look at a different type of problem. And these different types of problems are going to be kind of the opposite of what we just talked about here. So what if we have, instead of cold air that we need to heat up and humidify, what if we have warm, humid air, and we have to somehow cool that air and remove moisture from it? So the next thing that we're going to talk about is what we'll simply call dehumidification by cooling. Now, believe it or not, dehumidification by cooling happens all the time in air conditioning systems. Okay? In fact, I even alluded to this, was it weeks ago at this point? I had mentioned how in the evaporator of a refrigeration cycle, there's always going to be a little drain because the cooling system, the refrigeration cycle is so cold, it's going to actually cause condensation to occur. The air is going to actually drop below the dew point temperature in many cases, and therefore water vapor is going to start to condense. And that's exactly what we're talking about here. So let's say we first look at this on the psychometric chart, and let's say that this is my state point 1. When we talk about dehumidification by cooling, all we really have to do is pull heat out of the air. And as we pull heat out of the air, at first, there's not going to be any change in the specific humidity, right? The ratio of water vapor to dry air is not going to change. But eventually, we're going to hit the saturation line, right? When we hit the saturation line, we've reached the dew point, right? So this right here is the dew point temperature of state point 1, not dry bulb, right? The dry bulb is the actual temperature, not the same as the dew point. Once we hit the dew point, yet continue to cool, we know that the atmospheric air that we're cooling cannot hold that much water vapor, and the water vapor is going to start to condense out. So we're going to actually follow the saturation line down until we get to wherever our state point 2 is. Okay? So this is the process that is going to occur. If we wanted to show this, let's say on a air conditioning device, we'll just show it this way. There's going to be some inlet condition at state point 1. There's going to be some exit condition at state point 2. There's going to be some sort of cooling. And that's going to remove heat from the system. So some rate of heat removal is called Q dot out. And then as we drop the temperature below the dew point, some water vapor is going to condense into liquid water. So we're also going to have a drain down here at the bottom, and we're going to get water that drains out the bottom of this particular device. Okay. I might note that in your analysis, you are going to need to know what the enthalpy of that water is. However, it's not going to be a constant value. I mean, is it going to be at 0.2? Well, not really. The first of the water that condenses out of the air is going to have the dew point temperature associated with it. But as we continue to cool, and as the dew point continues to drop, the temperature of that drain is just going to keep dropping and dropping. In fact, what I would always note is that the temperature of the water is really just going to be the average between the dew point temperature and state point 2. Okay. So this is just the dew point plus the temperature at point 2 divided by 2. Okay, so that's going to be an approximate average. When you look at problems of dehumidification by cooling in the textbook, what you're actually going to see is that the author will give you an assumed temperature of the water that's draining out of this air conditioning device. Okay? If that's what's given to you, well, yeah, go ahead and use that data that's been given, but personally, it's not particularly accurate. So I would generally find the temperature of the water using this particular equation. So the question now is, what equations do we have to use for this particular process? Well, let's just start with the usual. This would be our mass and energy balance. So once again, we're going to start with our mass balance. We're going to start with our dry air. We note that, again, the flow rate of the dry air is not going to be changing, right? Yeah, there's water vapor condensing out, but the dry air component is not changing. So m dot dry air at 1 equals m dot dry air at 2, which then we'll just say equals the mass flow rate of the dry air. And then with regards to the water, well, we know that there's water coming in, but then there's, well, water coming in with the atmospheric air as water vapor, but then there's liquid water draining out, and there's water vapor going out with the atmospheric air. So we have m dot A and then times omega 1. That's going to represent the water vapor that comes in. What's going to go out is going to be m dot A times omega 2. So that's the water vapor that leaves with the atmospheric air. But then there's also going to be the water that has drained, and we'll just call that m dot W. Okay, so that's your mass balance for the air and the water. This equation we can modify a little bit. We'll just say that m dot W equals m dot A omega 1 minus omega 2. It's basically the same equation that was developed when we talked about humidification by heating plus humidification, but kind of in reverse, right? Here we're removing water vapor. Omega 1 is going to be greater than omega 2. In the previous example, we're adding water vapor. Omega 2 is going to be greater than omega 1. So the equation is similar, but it's certainly not an identical equation. Next, we would have our energy balance. However, I'm out of time, so we'll continue talking about this on Wednesday. Are there any questions on this particular topic? All right, so I'll see you all Wednesday. There are several exams up here, so if you didn't get yours, don't forget to pick yours up. I've got several homework sets from last week that weren't picked up on Friday, so please pick those up here as well. I'll see you guys next time. Don't forget to bring your homework with you on Wednesday when it's due. So.